Today we want to talk about the mean value theorem. Here's what the setup for the mean value theorem.
So, did you vote?
Yeah, a couple weeks ago, I believe. I even got the sticker. Oh, wait, check it out. I even got the sticker. It's in the back of my notebook. There we go. You'll vote. I'll tell you what page was I on now?
So, I actually did turn in my thing that I read to the vote.
All right, here we go. So like most things in, like most theorems for Calc 1, we need a function that's continuous on a closed interval. So let f be continuous on this closed interval. And also let f be differentiable on the open interval. So if we have a continuous and differentiable function on the interval from a to b, it needs to be continuous at the endpoints, does not need to be differentiable at the endpoints. The theorem is about stuff that goes on in the middle, but the endpoints are important. So if we have a function that is continuous on this closed interval and differentiable on the open interval, then there is some value on that open interval such that f prime of c is f of b minus f of a over b minus a. Pause for copying. Notice that the structure, this structure over here, f of b minus f of a, that's why we need continuity at the endpoints. Function needs to be defined, at the very least defined at the endpoints, but the function needs to be continuous on this at the endpoints. But we only need differentiable on the middle, and here's where we are differentiable at some point in the middle. So we have to be differentiable everywhere. So if we look at what's going on the left, we got f prime at c. That's the slope of the line tangent to the function at a point. Then f at b minus f at a over b minus a, that is the slope of a secant line connecting the two endpoints. So over here, we've got the tangent line, or the slope of the tangent line. And then over here on the right, we've got the slope of the secant line connecting the endpoints. And the claim is just that at some point, the tangent line is parallel to the secant line connecting the endpoints. So if we draw a picture, I'm just going to put one turn in. So here's a continuous function on the interval from A to B. This is a differentiable function on the interval from A to B. We got no sharp corners on the open interval. The secant line is the slope connecting these two endpoints. And the claim is at some point on the interval from A to B, some point strictly between A and B, there's a tangent line that's parallel to this. Now, if the function made a couple of turns, then there may be more than one, but it has to happen at least once. The theorem is not stating anything about where this point is. It's just stating that it has to happen. So that's one of the interesting things about this theorem. I don't know if that really counts as one of the interesting things about this theorem, but there are a lot of theorems of this kind, stating that there is something that exists. If these conditions are met, then this thing exists. The natural follow-up question is like, oh, great, where is that point? And it's like, well, we'll have to go and find that, but at least we know that we're looking for something. So there is some C in the open interval from A to B, where the slope of the tangent is equal to the slope of the secant. It could be more than one. So that at least one such C. There could be more than one, but there is definitely at least one. This helps us get a handle on what continuous and differentiable is about. We're going from point A to point B on a continuous and differentiable path. At some point, our instantaneous velocity is going to be equal to the average velocity. If I drive from San Francisco to Los Angeles at an average speed of 60 miles per hour, at some point I was going at instantaneous speed of 60 miles per hour. At some point I had to be going 60 miles per hour. So remember, we think of the secant line as the average rate of change. At some point, our instantaneous rate of change was equal to that average rate of change. You can't average 60 miles per hour without and skip going 60 miles per hour unless you're traveling discontinuously. In the category of there could be more than one, just imagine So here, we've got a function that is continuous on the closed interval from A to B and differentiable on the open interval from A to B. Our secant line is horizontal. So I had to make two turns, and I knew I would not be able to successfully draw. So I went for something simple. And there are more than one points. So the slope of the secant line connecting the endpoints is 0. And in this case, there are 2 points. Where the slope of the tangent line is equal to 0. So this is usually billed as like a very important result, which is why it's always fun after we get through a lot of mechanics to say, oh yeah, the mean value theorem. This is one of our most important results. Because from a student standpoint, it is not one of the most important results. We have never referenced it, but we have kind of referenced it. It's the reason for a lot of things that we take for granted, which is something that happens a lot in math. We take a bunch of things for granted, and then we start trying to dig out the reasons that those things are true. And the mean value theorem is kind of one of those. One of the important things about the mean value theorem, if you recall, when we started integrating things, we were just slapping a plus C at the end, and we kind of waved our hands at it saying, well, you know, the derivative constant is 0, so, you know, there's going to be some constant there. But with the mean value theorem, that guarantees that the most general antiderivative is that one with the plus C. That's the only thing that's going to be our antiderivative. There's not some other antiderivative running around that we have to worry about. So there are a lot of implications that are kind of baked in to the mean value theorem that we don't really need to invoke the mean value theorem all the time, but it's sitting back behind there once you start pulling back the layers, saying, why is this true? In Calc 1, if you start asking, why is this true? The answer has probably got something to do with the mean value theorem. This is also a variation on the intermediate value theorem. Which says if you go from point A to point B on a continuous path, then you hit every point in between. If you travel continuously from point A to point B, then you definitely were everywhere in between because continuously. If you are currently 5 feet tall, and at some point in your past you were 4 feet tall, then at some point you were definitely 4'6". You did not skip 4'6" entirely. You have to hit all the points in between. You did not instantaneously go from 4'5" to 4'7". That's not how people grow. Despite what the Sims tells you. You eat a birthday cake and all of a sudden, you're pretty much an adult. So in the intermediate value theorem, we would have, all we need here is a continuous function. If f is continuous on the closed interval from a to b, like we always need in Calc 1, and k is some value between f of a and f of b, then there is some c such that f of c is equal to k. 4 choice of variables there, or constants there. But if we go from down here at f of a to up here at f of b, and there's some value here in the middle, f of x equals k definitely has a solution, because we couldn't have skipped that point. We crossed every point in between. What you need is a picture of the mean value theorem. That when you think about, to remember the mean value theorem, in part, you need to remember the requirements. Continuous function on the closed interval, differentiable on the open interval. But then the mean value theorem is really this picture. It's often stated this way, but this is the picture that we need to carry forward. Slope of the tangent is equal to the slope of the secant connecting the endpoints at some point. Questions? Comment? Thought? Snide remarks? So today, the next assignment went up where it's a graded discussion where you want to look at the list of objectives upon successful completion of the course. Students will be able to, and then there were 11 things. Find a problem that you think is representative of at least one of those things. A better problem would be one that's representative of more than one of those things. Post about it in your in the discussion. Once you reply, then you'll be able to see other students' replies. So you get an idea about where things are going. If you come up with another one, you can, if one student's post makes you think of another problem, like if someone posts a chain rule problem, you think, but we also have to use all the rules of differentiation. So maybe we should have a product rule problem up there too. So we can reply to that. And then we could start building a problem set that's representative of what we need to be able to do moving forward. That makes sense? I want the point of the exercise, and I put this in the discussion. The point of the exercise is to get you thinking about what you know and what you know how to do, beyond just me handing you problems and having you react to them. That makes sense? That's the point of the exercise. I want you thinking beyond just like, oh, here's a problem, do this. Rather than just using your reaction all the time, I want you to use your action and your bonus action, put it in game term, to think about what you know how to do. You only need to make one problem. You don't need to make 11 problems. This is going to be the first round where you make one problem, and we're going to find out. It's like, clearly, we're all just thinking about finding derivatives. But that's information. That's the kind of information that I'm looking for. What are the, how am, I know what I think I've communicated, but I'm not really sure what I've actually communicated until I find out from the folks with whom I am trying to communicate. Does that make sense? So on one hand, I am outsourcing some labor to people that I don't have to pay, but I'm going to pay you with points. That's the only thing I can pay you with. I'm not allowed, I don't think I'm even allowed to just give you money. I don't think I am. Not like in official capacity. Like as just a human being, if I had like billions of dollars, I'd just be like handing money out. But I didn't win the $2 billion in the Powerball. So
No one winning yet.
no, I think one person did. I thought I saw an article where one person. For one person, $2 billion. Can you imagine that? That's ridiculous. Let's just hunt them down. I don't know. We already know. We already have the names of people with billions of dollars. So, I'm not sure where it was. Oh, wait. Is there an update? Someone in the chat knows? Someone in California won it. They're close by. We're gonna find out it was is a billionaire already. So I'm like, so what do you do? So well, I'm a hedge fund manager. I made billions of dollars in the 80s. What'd you buy a ticket for? I don't know, for fun. What are you gonna do with the money? Oh, sinking into another investment.
Yeah.
Anyway.
That was the one in Saudi.
Oh, I saw someone run numbers on like what you could do with like this is back when it was a $1.5 billion jackpot. What you could do with $1.5 billion if you invested $1.5 billion just into something simple like the S&P and it grew like at 10% and you took a dividend, it'd be like 75 million, just 75 million a year of forever money, of just not like 75 minutes subtracting from your total. That's how much that amount just grows every year, just for sitting there. You just get $75 million every year forever. And what can you, and like, what's $75 million? So let's break that down to half because you're going to pay taxes, because you're going to be a decent fucking human being. And you're going to say, you know, well, let's try to help each other. Let's put all the money together and see what we can do. So let's just say that's like, and round it a little bit to make it $36 million every year. After taxes, $3 million a month. Even in California, you could buy like 6 people, just buy them a house every month. You could take 6 unhoused people and just buy them a fucking house. And do that every month. Forever. Just forever.
I mean,
And have money left over. So you can also feed them. And probably pay for their health care. Maybe you're starting to see what I'm driving at. So anyway. And that's just one person with just $1.5 billion. That's just one person. Think of all the people that you know that aren't going to be buying a house. Start counting. Just start counting the number of people that you know that aren't going to be buying a house. And imagine, it's like, well, here are the first 6 people that I buy a house. Next month, here are the next 6 people. At a certain point, you just start running out of people that you know. Incidentally, the correct move after that is to move on to people that you don't know. Because the only the true test of our humanity is not when we're being nice to our friends, because that's easy. But start being nice and doing things for people you don't even know. And start doing those nice things when ain't no one gonna find out about it. You know what I mean? Because if you're doing it and you're having a press conference about doing it, you're not doing it because you care. You're doing it for the clout. Like if the only reason you don't go around murdering people is because you don't want to get caught and thrown in jail, that doesn't make you a good person. That gets you to 0. It's like, well, I didn't murder anybody yesterday. I don't know about y'all, but I didn't murder anybody yesterday. Where's my reward? No, that gets me up to 0. That puts me even. You know what I mean? So all these billionaires, I'm going to give away half of my fortune. How about this motherfucker? We're going to come take the rest of your fortune. Like Patagonia dude. Have you heard about Patagonia dude? Oh, he's an accidental billionaire. Bullshit. No one's an accidental billionaire. He's not taking his money and giving it to charity to do charitable works. He's buying clout, political clout, for his family forever. That's what he's bought. That's what the charity is for. So that's just a case of good marketing. At least people like Elon Musk and Jeff Bezos have the balls to say, we're going to fly to space. Your employees are pissing in bottles. Yeah, fuck them. I'm flying to space. Woo! You know what I mean? Anyway. All right. So you can tell that I'm not the one that won the 1.5 or the $2 billion. You know how you can tell? Because I'm here today. That's going to do it for today. Think about the mean value theorem. Just wanted in the back of your mind. I'll see you all on tomorrow, but have a good day and thanks for playing.
All right, I'd like to like a couple of pounds. I'm saying, isn't that such a